Good afternoon. Let's start the lecture. Okay, just a quick word that we're going to have our second quiz during next week tutorial. Okay, so quiz number 2. Go to your tutorial section next week to take quiz number 2. The next second quiz will be on double integrals, basically. Okay. I plan to use a question from last year final exam for our second quiz, the double integral. Okay. That's the second that question turned out to be a pretty challenging one actually for last year. So let's see how you can tackle it, given ample time with open discussions and some hints from the TAs. See if you can do that. Okay. Yeah. Okay, so today we're going to continue on the double integral. We'll talk about some applications of the double integral. Okay, so particularly some of the applications shown at here will be quite useful to mechanical students, and also some of the formulas probably we will see that in the future statistics and probability courses. Okay. Okay. Okay, so is that better? Yeah. First application of double integral. Let's take a look at the easy one here, okay? The first is to find the area of a region R. So we probably have a region R right here, and you're interested in, so what is the area of this portion? In terms of double integral, it's fairly easy. Remember the double integral itself is this. This is double integral. Now if we set f of xy equal to 1, then basically we end up with a double integral like this. Okay? Yeah. And we know that in single variable, you know that single variable integration of t is t, right? So basically, if integrating anything at here, you get that thing. Okay? Yeah. So in this particular case, double integral, so you would expect to get what? To get the area. So that's basically, you get A out of here. Okay? So that's a simple application of using double integral. Okay. So all you need is to integrate over the R, you get area. And let's take a quick example right here. So let's say I have a region. So this region is bounded by two curves. One is y equal to x, and the other is y equal to x squared. And the question is, what's the area bounded by the two curves at here? Right? Okay? Yeah. So according to the formula, it's pretty simple. So the area equal to this. Okay? And dA, we know that it's basically dr dx. So when you do double integral, you need to determine an order of integration first. You can either dx first or dy first, doesn't matter. And in this particular case, it doesn't make much difference. You can integrate either one is fine. So let's say I'm going to integrate with respect to y first and then x. So then what you do is, as we learned, you draw a narrow line in the y positive x direction across this region R. Okay, and then the first contact is y mean, and second contact is y max. So in this case, first contact is x, and second contact is x squared. And then you sweep this. Pardon? What? Oh yes, sorry. Yeah. So lower bound is x squared and the upper bound is x. Okay. And then you sweep these arrow lines across this whole region. Apparently, x mean 0 and y mean is this point, which is the intersection between the two curves, and which is 1. Okay. So that's it. That's basically the layout of this double integral. And this is a pretty simple double integral. You can integrate that, and you will end up with 1/6. Okay? Yeah. There's no trick added here in this double integral. Okay, so that's area, right? That's area. The next simple application is mass. Okay. So particularly, let's say maybe it's a mass of a thin plate. And the thin plate, essentially what we're saying is the plate is defined by a region R. Okay? So this region R represents essentially the thin plate. Why is it thin plate? Because the thickness is so thin, we can neglect this thickness of this plate at here. Okay, that's what it means. Because if the thickness is not negligible, and we actually will have, if you're talking the mass of this plate, then we're actually going to use the so-called triple integral now in the next lecture. All right? Yeah. When we talk about mass, and basically we often have to define a density function first. Okay. So density is defined as let's use a delta to define as density. So that's defined as the mass, total mass basically, over this unit area. Okay. In other words, if you remember, when we often say delta m with a small mass equal to delta this density times the small area. Okay, so if I have an area here, and then there is a very small area, delta A, okay, then the small mass for this small area is delta times delta A. Okay. So if this is the mass for this small patch at here, then we add all of them up, we get the total mass of this region R at here, right? So basically total mass, okay, when you add them up, okay, it's essentially give you a double integral delta, okay, dA. Okay, so the only difference between this this formula and the previous one is you get an extra function delta here. So this delta function is actually, there's no difference from my previous one, basically say, oh, R, f of x, y, dA, right? So you see, this is no different. Basically, this delta here is that function f of x, y we have been writing with, right, all the time. So that's mass. And if you have a delta function density equal to 1, right? If basically delta equal to 1, and this mass basically turned out to be what? This mass delta equal to 1 meaning uniform distribution, and this formula actually turned out to be area, right? It's the area. Okay? Yeah. So that's number 2 application. This is very simple. Number 3. Okay. This is a sort of an enhanced application now. We call that average value of a function fxy over region R. Okay, average value of fxy over region R. So let me start with a simple idea first, and then we'll derive to this so-called average value of a function f over region R. Okay. Yeah. Now, if you remember, if I give you a set of data, okay, so let's say this data is A1, A2, and maybe up to AN. So you have a n number of numbers at here, and then the question is, so what's the average of this set of number? So everybody knows, right? Average equal A1 times plus A2 plus AN over A. So that's the average for this set of data. Okay? Yeah. And this is a discrete, right? This is discrete. So you can think of if you have a region R, basically you're going to take as many as possible inside this region R. Take all the numbers and certain kind of numbers and then divide it by n. You get an average here, right? Yeah. So we have to go from a discrete idea to a continuous idea here. Okay. So now let's extend this average idea to a more specific case at here. Okay. So let's just say I'm gonna let this function f, give it a certain specific meaning here. I'll let it be height. Okay, I'll let it be height of a sort of a cylindrical object. So what does that mean is, so I'll draw something at here. There is a region R at here, and then there is a certain kind of a cylindrical object. Okay, basically that object is defined over this region R. Okay, yeah. So there's a surface on the top of it here. Okay, and the surface that here represent, you give any value from region R. Okay, you give any value of region R, you get certain points here. So that's not exactly a kind of cylindrical object, but it's basically vertical, and there's a top and there's bottom, right? Yeah. So then, if you're looking at this point, and then there's a height at here. If you're looking at this point, and there's a height at here, and that height, is basically described by this function f of x, y. Is that good? Yeah. Okay, so then the next question is, what will be the average height, right? What will be the average height for this given object, over this region R? So you have so many heights here, right? The average height basically means you want to add, here's a height, here's a height. How many points? I don't know, infinite number of points. You add all the heights together, and then you divide it by the total number. You get average, right? Yeah. But doing discretely, essentially. It's impossible, right, to get an accurate height. Okay, so, but let's start from this discrete case study here, right? Yeah. So I'm saying is the average height, average height equal to all the height, you add all the height to get add all them up. Okay. So maybe there are how many heights there may be n number. You picked n number of points inside the region R. Okay, so you picked a number of heights, and then you divide it by the total number n, so you get the average height. That makes sense, right? Nothing tricky here. So there are n number. You picked a number of points, and then you add all the height up and divide by n, you get average. Okay, so now I'm gonna manipulate this slightly at here. I'm gonna let's say for this particular point, right? There is a patch, delta A. So basically, around each point that you picked, there is a delta A associated with it, area. So I'm gonna multiply the delta A at here, So multiply it at here. And if I multiply it here, so which means I had to get rid of it to make sure that I'm not changing the original expression here, right? So what does that mean? So that means I need to, basically get rid of this delta A at here. Okay, so that's the operation, right? Okay, that's operation. Okay. So and 1 over n times delta A and multiply by this chunk at here. Okay, let's put this chunk. Okay, so now, if I look at basically the case, if I'm gonna let n go to infinite, if n goes to infinite, so what does that mean? If n goes to infinite, what does n times delta A give you? N goes to infinite, the delta A will become dA, right? Become dA. So you have a infinite number of this small dA here, then you basically n times all of them. Basically, you're adding all the small patches together. You end up with actually what? The area, right? So this denominator here, as n goes to infinite, this n times delta A will become the area of this bottom region R. That make sense? So the n delta A will become the area, of R. Yeah. And as n approached infinite, what happened to the summation sign? The summation sign will turn into the integral. And this delta A basically dA with dx dy. So this h height now will become 1 over the area, and then double integral R f of x, y, and dA. So that's what happens when n is going to infinite. So this one here is basically we're looking at, okay, for the third application, okay, for third application. So if you look at this, formula here, that's essentially what the title is saying: average value of this function over region R. Okay, so if you think carefully here, average value of this function over region R. See, that's exactly what happened. F of x, y, you're picking, because you're picking every point in the region R and you plug it into the function f. Okay, you add them all up and you divide it by the total area, and that gives you this so-called average value, okay, of function over region R. This is actually kind of so basically in actual application, it doesn't necessarily you have to always stick to the height, and it could be something else. I'll show you an example shortly. Okay, yeah, but in general, essentially what we call the average value of function f over this r, okay, so maybe I'll let it equal to f bar, okay, and that equal to the formula that we just derived at here, okay, 1 over area. Okay, equal to this. That's the average concept. So if you look at this one here, basically that gives you a sense of abstractness. Get rid of the abstractness of the mass formula, right? Divided by area gives you average concept. Okay. So for example, if f of x, y, okay, now f of x doesn't represent height anymore. Maybe f of x, y is the temperature over this same plate or a region R. Okay, so it's a temperature distribution. Okay, it's a temperature. Then when you plug it into this formula, then you're supposed to get what? You're supposed to get average. So if you get rid of the value, average temperature value, right, over this region R. That makes sense, right? So if this is the temperature, then F bar is average temperature. Okay? Yeah. So basically that kind of idea, right? In any physical quantities that you are using f of x, y to represent, and if you plug it into the formula, you get the average value of that quantity. Okay? Yeah. So let's see an example right here. Okay, suppose that I have a region R, which is a circle. Okay, and this is R, x squared plus y squared equal to less than a squared. So that's the region R. Inside the circle, okay, and the same plate described by a circle. Now what we want is, we want to find the average distance, okay, average distance from a point, okay, any point, okay, inside R, okay, so from a point inside R to origin, okay, to the origin, okay, so you pick a point at here, and then you get, okay, a distance, right, between that point and the origin. You pick another one, you get another distance. So the question, what's the average distance, for all the points, right, inside this region R to the origin at here? Okay, that's the question. Okay. Is that good? So you're looking for average distance. If I wanted to use this formula here, and basically we need to formulate this question so that it can fit into this formula. So in this formula here is average value of this average value described by this function over this R. So now what's the value? The value is the distance. So basically, this function f of x, y at here should be what? Should be the distance. Okay? Should be a function describing a distance. Okay? It's a distance from arbitrary point to the origin. So given a point P, and what is the distance of that point P to origin? It's as simple as square root x squared plus y squared, right? Yeah. And we need an average value. Basically, this is your f of x, y here. Okay, f of x, y. And we need to find, the average distance, or d bar, right? And over this r here. Okay. That's the formulation, basically, from this question here. Is that good? Yeah. Okay. So now, once we have the problem formulated, and all I need is to plug it into this formula here, right? I guess what we can do is we can look at it in separates, but you can put everything together. So average of the d average equal to 1 over this area of the region R, and then times the double integral. F of xy is x squared plus y squared dA. Okay, that's the expression that you need to evaluate. So area of R, again, that's too simple. It's a circle, so area of R is pi times the radius squared, and the radius here is A, right? Is A. So area is, right, this quantity is 1 over what? Pi A squared. Okay. And the double integral. Now this is where you gotta practice now. This is in Cartesian coordinates x and y. So remember, when we see a circular kind of area, so chances are what? The polar coordinates will probably come in handy, right? Will probably simplify your calculation. So I'm gonna evaluate this double integral using polar coordinates. So to evaluate the polar coordinates, what do? We're going to replace the x with r cos theta and y with an r sine theta, right? Yeah. At the same time, the dA will become what? Exactly, r dr d theta, right? Yeah. One student came to me this morning, couldn't figure out the right answer because they didn't have the r at here, right? Yeah. So you gotta make sure you write 10 times to get that right. Yeah. Okay. So second of all, plugging the x over here, y over here, and the simple trigonometry. When you plug it in, what do you end up with? R squared cosine theta squared plus sine theta squared. So this plus this is 1, and root r squared is r. So together you get r squared. Okay. And for the limits, because it's a polar coordinate, and the region, this is the region here. So as we have been saying, what do? You draw a reading lines starting from origin across the region R. First contact give you R mean. Second contact give you R max. First contact is the origin 0. Second contact is the boundary A. So R mean is 0 to A. Then you sweep this reading line here across the whole region R to find the bounds for theta. That basically sandwiching this region R here. So in this case, the whole circle. So you're going to sweep from 0 for a whole round, no redundancy, right? So it's 0 to 2 pi. Okay, is that clear? Yeah. So once you get this, that's pretty straightforward now. And pi a squared, 0 to 2 pi, 0 to a, r squared dr d theta. Okay, yeah. So it is double integral, but actually it's more of a 2 single integrals. So inner integral, once you finish the inner integral, there's no theta anymore. So theta basically is a 2 pi. So altogether, 10 seconds. Okay, you try this one out. See what do you get. Pardon me? Figure?
Oh, nothing. Just solving it.
Okay. And you get it? Yeah. Right. 2a over 3. Okay. So that's the average distance in a unit circle. Not a unit circle. In a circle of radius of a, the distance from any point to the origin. So now, the next thing is I want to show you. If I give you a different problem here, you actually will see you'll get the same answer, huh? If I see a different problem like this, here's a question. Okay, can you find average height of the cone z equal to root x squared plus y squared above a disk x squared plus y squared less than a squared. Okay, so there might be a question like this. Find the average height of the cone above certain disk, which is this. Okay, so of course we haven't in the triple integral we use this quite a bit here. You might wonder why this is a cone. Well, yes, it is a cone here. If you draw them out, this cone is basically like this. Okay, it's actually an inverted cone. Not inverted. It is a cone anyway, right? So this is the cone here, and the question essentially, you pick a point, right, on any point essentially on the surface of the cone and try to find the average height, right? Okay, of every possible here. But this is the cone above the disk x squared plus y squared less than 8. Because if I don't have a disk, if I don't see over a certain disk or over a certain region, so that cone can extend beyond to infinite, right? So now if the question define certain region, so this is basically this region or the disk at here, right? This is the disk here. So that cone, right, is restricted, okay, to this region R. Okay? Yeah. So the cone maybe it will extend anywhere beyond here, but you're really looking at is basically only between the bottom region R and this top there. Okay? Yeah. Is that good? Yeah. So before we move on here, let me ask you a trivial question here. Okay, very trivial question. Suppose this is vertical, this is vertical. What would be the z value at here? What would be the z value at here? It's basically, this is a top flat surface, and it intersects the z-axis, right? So what would be the z value? Essentially, the top one is a plane. It's a z equal to something, right? Z equal to something, it's a plane. So what would be the value, constant value then? A, exactly, okay? Yeah. So this bottom here, right, this one here is basically like a level curve, right, of this surface. And the level curve is z equal to a. So when you plug a equal here, what do you get? A equal here. So that you get basically x squared plus y squared equal to a squared, right? And that's the bottom of disk, okay? Yeah. So that's actually, in the triple integral, later you will probably make use of this simple knowledge, okay, in quite a few different cases. Okay, so now if I back to this question here, what's the average height, right? What's the average height of this cone to origin? To the where's the power bar? Right, average height. So if I'm looking for average height and over this region R, if I formulate this question, what does that mean? So area of R, double integral. So what would be the function at here then? What am I integrating? the function is a height. Which is a height? Height is basically this guy, right? This guy here. That's the height. So, okay, yeah. Now, if you compare this formula with this expression we just derived here, and compare this one to the example that we just did here, is there any difference? And there's no difference at all, right? No difference. But of course, there is a difference. Basically, the description of the problem is different, right? Yeah. But in terms of the calculation or evaluation, it's the same thing. Okay? Yeah. So that's the beauty of math. You have a generic expression here, and you can use that in many different situations. Okay. So that's number 3. Let's look at the number 4 application. Any questions? All good? Okay, yeah. So number 4 is so-called weighted average of this function f. So idea of weighted average, okay, is pretty simple in terms of the discrete data. So let's say given a discrete data x1, x2, and up to xn. Okay, so you have a n number of data. And now if you wanted to calculate the weighted average, so what you're saying is, at the same time, so each one of the data has a different weight. So one of them probably carry a bigger weight, and one of them probably carry a smaller weight, right? Yeah, that's a very common idea. So if you define the weight as W1 and W2 and up to Wn, associated with each one of the data here, okay, then in terms of average, okay, the way to calculate the average x bar, right, it's basically going to be W1 times x1, W2 times x2, and up to Wn times xn divided by W1 plus W2 and Wn. So that's how you calculate this weighted average of this function f. In probability concept, this is a very common concept. So you have a Gaussian distribution. The data has a different weight at a different location, right? When you calculate the average, then you need to multiply the so-called probability function. Okay, yeah. Okay, so same thing. Here we have this weighted average function. So let's maybe use a generic question here to talk about this. Let's say I'm gonna let f of xy be weighted by the mass of the plate. At each small area delta A. So basically it's like this, right? So you have a region R at here, and we picked a small patch. We denote that as delta A, and this function f of xy is defined with this region R. So now we're going to weight this function f. So maybe there's a function value defined in here, but we're going to weight it by the mass at this location. So what does that mean is you have this function f. That function f, maybe this location is x of k, y of k location. So you have a value over there, right? You got a value here. Then we're going to weight this one, or scale it up by its mass at here, by its mass. So a delta mass, as we learned, we can describe this delta mk using this delta A and times the density delta. So delta, the density, times this small patch area, give you this delta mk. Okay, yeah. So you see that weighting, can be described by this idea here. And then, if we're talking about the weighted average, then the weighted average, the F, okay, just like this one here, right? Just like this. Weighted average is this times altogether divided by all the different weights, right? All the different weights. So in my particular case, what are we adding together? On the numerator, you're adding, n number of points like this, n number of expression. On the denominator, you're gonna add delta m1 plus delta m2 because this is a weight, right? This is a weight here. So basically, you get the mass of R, right, at the bottom here, and at the top, you get this double integral. Okay, you get this double integral here. That's weighted average, right? So if you compare this weighted average expression with the previous average formula, the difference is now you have a delta function showing here. So this delta function in this case, I said it's a density. But in practice, or in generic case, you can consider it as a general weight, right? General weight here. And this becomes a mass of R. Right? Previously, this is an area of R. Why does it become a mass of R? Because area R times the density, you get basically the mass of R, right? Yeah. So this is basically the weighted average. Okay. Yeah. Is that good? Okay. So from this weighted average, very naturally, we can extend to two important mechanical property, okay, of a certain object. Okay. So the fifth application is so-called center of mass. So I think you learned this in your first year, your center of mass, and it's just giving a certain object, where is the center, right? So in this case, we're focusing on 2D, so we're focusing on a thin plate. Basically, where is this center of mass like this, right? Center of mass. So we call that Cm, okay? So center of mass can be derived very naturally from this expression, okay? So if you look at the expression here, I'm going to do a very simple substitution, okay? So I'm going to let f equal to, I'm going to let this f of xy equal to x, okay? So let this f of xy equal to x. Then I'm going to sub this f of xy into this expression right here. So the left side will become what? 1 over the mass of R, double integral. So this one will become x delta dA, right? Delta dA. And the other side, this is f bar, the average value, or the so-called weighted average value for the function f. Right now, the function f is x. So this side is simply x bar, the average value of this x value. So what's the x value? Basically, you pick any point up to here, so there's x. You pick another point here, there's another x. So essentially, that's weighted average, right, of this x. You get x bar, and that's the center of mass for the x component. So similarly, if you let f of xy equal to y, okay? If you put y here, then you get what? Y bar equal to 1 over this mass of R and times double integral and y delta dA. So the delta function could be a function of x, y, more specifically, so I'm skipping this one here, okay? So it doesn't matter. Okay. So that's center of mass for a thin plate. Okay, center mass for thin plate. Now, often in time, okay, this portion right here, okay, so this portion is defined as a so-called my, and this portion is defined so-called mx, okay, mx. Now, as a matter of fact, I'm not sure if you learned this or not. For this particular two portion, if delta equal to 1, okay, So basically a unit density, then you see that delta equal to 1, so this is gone, right? This is gone. So you have an expression like this. So mx equal to this, and my equal to this, right? To this. So these two quantity, okay, there's a name, it's called first moment of area. Okay, first moment of area. So why is the moment area? Because we're talking about the cross section here. Okay, cross section is the first moment. Okay. So you probably think, oh, we must have a second moment area. Yes, so that's what we're going to talk about here, right? So there's a second moment area. Was that good? So before we move on, maybe I'll show you an example right here. Okay. Okay, so here's an example. And I have a region R, which is defined by two curves. One is y equal to 1, and one is y equal to x squared. Okay? And region R is this. Okay? So the question now is, what is the center of mass for this one here? And density for this plate is defined by this, delta xy equal to y plus 1. Okay? Yeah. So it's not a constant density. It's varying. And then we wonder where the center of mass is for this region R. Okay, so we just need to apply the formula x bar and y bar. Okay, yeah. So in order to apply this formula, this x bar, y bar, if you look at it, okay, so we actually need to do two kind of calculations. One is we have to calculate what's the mass of the thin plate, and the other is we have to calculate this double integral, and then we divide this each other, so we get x bar and y bar, right? Yeah. So let's calculate the mass of R first. That's our second application, right? Second application. So we're talking about mass of a thin plate. So when you calculate the mass of a thin plate, it's a double integral, and then you have this density function right here, and dA, right? That's the second one. So if you see the second application, so that's this one here, right? That's this. Okay. So now I have my density given, which is y plus 1. And this is a Cartesian. There's no circle involved. I think I better stick with the Cartesian coordinate. So all I need to do is to pick a direction of integral here, right? Order of integration. So I think it will be easier to integrate with respect to y first, because what? Because I just have to draw one lines here, you know, minimum and maximum. So actually, it probably doesn't make much difference. If you do x first, here's the first contact, here's the second contact here, right? Yeah. You know what? Maybe let's do this in x direction here. If I do the x direction here, so dx, dy. Okay? So what's the x mean at here? Pardon me? Negative y or negative? So this is y equal to x squared. So which means what? X equal to positive, negative, root y, right? Yeah. So for this side here, it should be negative this. For that side, it should be this, right? Yeah. And then you sweep this line vertically up and down. Okay. So basically, bottom bound is 0 and top bound is 1. Okay, that's it. Okay, so this is a pretty simple calculation. If you calculate this one, you should end up with 32 over 15, okay, for the mass. Okay. There's no sine or cosine involved, you know, just typical integrals. Okay, so now I need this mx, my quantity. Okay, these two quantity here. Okay, these two quantity. So let's try mx first. So mx double integral. So what am I integrating? X times the density. So x times the density, and then d. This is my, right? X times density is my. Okay. X times density and dx dy. So let's say I'm still gonna do the dx first. Okay. Let's still do the dx first. So dx here, negative root y, positive root y, and y is 0 to 1, same integral limits, okay, as the mass. Okay, yeah. Okay, so same thing. You carry out this integral is nothing tricky here. Just when you integrate with back x, you treat y as a constant. Keep going like that, right? Yeah. So now you'll see this is 0. Okay, you'll get a 0 right here. Okay. So now I'm gonna teach you a trick right here. Okay, a trick. But this trick, you shouldn't rely on this trick too heavily, or if you're not too sure. Okay. So the trick is, if you remember, in single variable, if you're integrating from, let's say, negative a to a for a certain function, okay, for a certain function. So negative a to a and f of x, let's say dx, right? Yeah. Under what condition this guy is 0? I mean, there's a condition. This guy is 0 if what? If f of x is so-called odd function, right? So basically, odd function meaning f of x equal to negative f of x. So what does it mean is basically the area, right? This is odd function. The area is negative and positive. They cancel each other. You get a 0 area, basically, right? Yeah. So same thing to this double integral. Actually, you can also use this idea. Now, if you look at this inner integral here, okay, the inner integral. If you don't trust me, in the first of all, maybe you can carry out this inner. What's the result of inner integral? This x. You treat this y plus 1 as a constant, right? So what does the x become now? It becomes what? 1/2 what? X squared, right? And times y plus 1. And what's the integral limit? Negative root y to root y. And guess what? What do you get from this inner integral? 0, right? You plug this in, it's all positive. So it's all the same thing. So a minus a is 0, right? So the same thing here. So you see this x here. So right now, the integral, this is a symmetric. You see that, right? It's a symmetric here, basically. It's a symmetric region with respect to y-axis. And at the same time, you are integrating with respect to x first. You look at this function. If you forget about the y here, y plus 1. The y plus 1 you consider as a constant, right? Consider a constant when you do the inner integral. The x function only. So when you have a f of x equal to x, what's this function? This is an odd function, right? This is an odd function here. So this is why you can make use of so-called, basically use of a symmetry here to simplify your integral often in time. But my caution for you is, you don't rely on this if you're not too sure, right? You basically you want to calculate this because maybe it's not 0, right? Maybe you're wrong. Okay? Yeah. Was that good? But it's just a note though, right? Okay, so you can do the same thing for mx. Okay, it's negative mx, so it's y times y plus 1. So y times the density function and dx dy. So maybe I'll do the dy dx in this case. So if I integrate with respect to y first and then dx, so let's see what's the integral limits now. If I do the dy first, the first contact is at y equal to x squared. The second contact is at y equal to 1. Okay, so this is a y. This is that work? It still works. So this is x squared and to where? To 1, right? Okay. So x limit is you sweep this line across the whole region. So basically, one bound is here, one bound is here, and guess what? The intersection here is -1, and intersection here is 1, right? So -1 to 1. Okay. So now this one you won't get a 0. Okay, you won't get a 0 here because that region is not symmetric to x-axis. So you will end up with 48/35. Okay, 48/35. So x bar equal to my equal to divided by the total mass, and x bar is 0, and y bar equal to mx over the total mass. So this number divided by this number, okay, and do a little simplification, you end up with 9/14. Okay, that's the center of mass for that region R. Okay, is that good? Yeah. So typically, if there's any kind of question like this, and then you should be okay. Okay. Okay, so that's number 5 application, center of mass. Any questions? Okay. Number 6 application is the so-called second moment of area. Most of the time, you actually probably don't hear that. What you hear is moment of inertia. Okay, moment and inertia of the area. Okay. So I'm saying you probably also see different name, and one of the name is called second moment of area, or sometimes just simply area moment of inertia. Okay, area moment inertia. So moment of inertia is a one single important mechanical concept, and also for civil. Basically, whenever you have an object, you have a moment of inertia, right? But to simply put it, mass, what exactly is mass? So what does mass represent? Yeah. Exactly. Resistance to acceleration or to certain translation motion, right? Yeah, so this is basically resistance, okay, to a certain kind of a translational motion. So then, second one is, what about moment inertia now, right? Now, whenever you talk about moment inertia, it's a quantity associated with an axis of rotation. Okay? So here's an object, here's the axis, and now you want to rotate the object with this axis. So then the physical meaning of the moment inertia will be, just like the mass, it will be what? It will be a resistance to rotation about that axis. Okay? So basically, if this is the object, you want to cause a translational motion. So what do you apply? You apply a so-called force, right? So you can cause a translational motion. Now, if you're heavy guys, you have to apply bigger force. And if this is an object, you want to cause a certain rotation, and then you have to apply so-called, not a force anymore, it's called a torque. So if this is a big things with a big moment inertia, then you have to apply a bigger value of the torque, right? So basically, resistance to rotational, okay, motion. Okay, that's moment inertia. Okay. Now, moment inertia, we here I'm specifically saying this is moment inertia of the area. The reason is because we're dealing with double integral. We're dealing with this thin plate, right? And we consider this is the area defined by the region R. Now, when you go to triple integral, basically you go to an actual 3D world. You have a 3D object. That we get rid of this area. We just call it moment inertia of that object. Is that clear? Yeah, that's the difference here, okay? Yeah. But the idea is the same thing, okay? What's going on with this thing? Right, power? Yeah, I think so. Okay, is that better? Is it? No? Let's try this one. Can you hear me? No? Knocking? No? Okay. Still works. Why does it not work? The next time I think I should bring my own batteries. Pardon me? Okay, let's see if this one can last until the end of the lecture here, okay? Okay, so let's talk about moment inertia here, okay? I'm gonna basically start from a simple case study here. So moment of inertia, okay, with respect to an axis, okay, going through origin, okay, going through origin. So what does that mean is basically, I'll illustrate this idea here. So let's say I have a point mass. First we start with the simple one here. With a very small point mass here, so the object is described by a point. And this point mass is moving, and it has a certain distance to the origin right here. So you have an axis passing through the origin, and which is perpendicular to the plane, okay, to the page. Okay, so this thing will rotate about this axis. So what do is we talk about very generic case here. So let's say at this particular instant, it's moving, okay, with a certain velocity, linear velocity v, and after a little bit, it's coming, okay, after certain delta theta, okay, it's coming to this location right here. So that's basically sort of like the trajectory of this rotation right here, okay? Yeah. So not necessarily it's a circle, okay? So it could be, there's always an instantaneous so-called angular velocity or speed. So now let's look at the velocity here, or the speed. Speed v, okay? Speed v and here. So when this small mass m travel from this location to this location, it traveled a distance described by arc AB, right? Arc AB. And we know that the speed is the displacement divided by the delta time. So the arc length AB is approximately r times the delta theta. And then delta t is supposed to be the time goes from A to B. So that's the speed, right? That's the speed. Then if you take delta theta to be very, very small, then the V will be approximately r d theta over dt now, right? D theta over dt. Okay? So that's speed equal to r d theta over dt. And we learned, the derivative of this theta angle is actually called what? Omega, right? That's called angular speed. Okay? Okay? Okay, so back to the linear velocity or linear speed v at here. Kinetic energy is equal 1/2 mv squared. Kinetic energy for this point mass. If I sub this r omega into here, I get 1/2 m r squared omega squared, right? Okay? So kinetic energy, I'm going to use a different symbol to represent the kinetic energy. We let a symbol r naught, I naught, for this mr squared. Okay? So this I naught at here is basically the moment inertia for this m, point mass m, with respect to the axis going through the origin O there, okay, perpendicular to the page. Is that good? Yeah. So basically we end up with I naught equal to M R naught. And that's for point mass, right? That's for point mass. But we're more interested in is not just the point mass. We're probably interested here is a region R. And what is the moment inertia for this region R with respect to an axis going through the origin here? That make sense? Yeah. So technically, what do? You can pick a point just like that, point mass, calculate that moment inertia. Give another one, calculate. So you add them all up, you get a total moment inertia, right? So that's approximation idea. Basically, what you do is you get, okay, for each point you get a delta mass. So let's say for this location there is a delta mass which could be approximated as the point mass. Sorry, this is not working now, so I just had to shout. So you have a delta mk at here. So you have a delta mk. Oh, that's good. So you have a delta mk at here, and that equal to the density times the delta A, right? Times delta A. And the moment inertia for delta mk, according to the formula that we just derived, it's a point mass. So basically, it's what? It's delta mk times rk squared. Okay, the point mass with respect to the origin, right? With respect to the origin. Okay. So now what I need is, I need basically the total, all of this delta mk, right? Add all of them, I get this moment inertia for the region R with respect to the axis passing through origin. So then the total, okay, moment inertia is, okay, double integral now. So R square delta dA. See, right? That's basically directly coming from here. Right? This is the total moment inertia. What is delta? It's the density describing this plate. What is R squared? It's the distance from any point inside this region R to the origin, right? That's R squared. And R is this. Now, we normally represent this guy using J. Okay, I'll explain why. We normally using J. You probably say, well, why did you use I there, right? How come you're using J? We're using J for moment inertia when the axis of rotation is perpendicular to the area or the cross section you're looking at. Right? Can you see that? The axis of rotation is perpendicular to the page, right? So now next one is, I'll show you another one. We use I. We use I if the axis of rotation is in the same plane as the cross section. Okay? Yeah. Is that clear? That's basically J equal to this. Now this one here, because this is basically the moment inertia with respect to origin, axis passing through origin. So a lot of time you will see this is also called polar moment of area, okay, or polar moment inertia. Okay. There's so many names, some people use differently. Okay, but the polar essentially, because you get R squared, that's the distance to the origin. Okay, so to extend this application just a little bit here, because this is the moment inertia with respect to axis passing through origin. How about the moment of inertia, okay, with respect to x-axis or y-axis? Okay, so x-axis or y-axis. So here's the idea. Basically, here's the area. Okay, and you want to cause this cross-section R to rotate about the x-axis or the y-axis, and how hard or how much torque that you should apply to cause certain angular speed. So you have to know the moment inertia about that axis first, right? Yeah. So same thing, you see this r square here represented is the distance. See here, right? This r square, or the r here. So this r here represented is the distance from a point to where? To the axis of rotation, right? From axis to rotation. Now the axis rotation, suppose we're looking for axis rotation is x. So if I pick any point, what will be the distance to that axis from here to here? What's the distance? X coordinate or y coordinate, right? Just the y coordinate. So basically, if I'm looking for moment inertia with respect to x-axis, now I'm going to use I now. I call it Ix, okay? And that's basically what? It's a double integral. That r squared will become the distance from any point to x-axis. So basically become y squared. And then you probably will time the whether you have it or not, the density, and then dA. Okay, that's very simple, right? So Ix is related to y. And then similarly, if you're saying, what's the moment inertia about the y-axis? So x squared. Okay, yeah. So that's it. That's the moment inertia, like this idea here. Okay, yeah. Now let me ask you a very interesting question here. You probably learned in the first year, okay? What does I times omega give you? No? This is called angular momentum, right? This is called angular momentum. Just like the linear case, what does m times v give you? What is this? What is this called? Linear momentum, right? Okay. So here's a question: how does the figure skaters, skate people, make the rotation or spinning faster? No magic. Yeah. So what did she do? Fin, yeah.
They bring their weight closer to the center, reducing the radius.
Yeah, so what did they do? Show. Oh, yeah, they do this, right? So what happened when you do this? So, they begin with, something like this, and then they do this. So when they do this and this, which one has a higher moment inertia? The close one, right? So in the first year, you learned one thing called what? Conservation of this angular momentum. And conservation angular momentum basically states when you have a frictionless or almost frictionless case, and basically there's no external torque applied, and there should be a conservation of this angular momentum. And that's pretty much the case when you are on the ice. So if this is conserved, then in order to increase the omega, you have to reduce the I here, or the other way around, right? Yeah. So basically, when you have this, bigger I. When you have this, smaller I. And that's what happens, physics. As a matter of fact, people did a little very approximate calculation. When you do this to here, theoretically, you could increase 12 times in terms of speed. Yeah. But of course, practically, probably not much, right? But theoretically, you can increase 12. And this is actually why that the figure skates, the girls are all small girls, right? Smaller. And then they also don't do that when they're getting older, right? It's in the 14, 15, they're in the best stage. So anyhow, that's the one of the physical things can explain from moment inertia. Okay. Yeah. Okay. So we're almost running out of time, but I do have one more interesting thing here. So I wanted to bring the math into theories. So let me ask you. Let's do an example here. Here is a plate or a disk. Okay. What is the moment inertia of this disk with respect to the axis going through this origin O at here? So I can call it I naught or J, doesn't matter, as we derived. Okay. Yeah. So moment inertia of this plate with respect to the axis, if you draw it in a 3D case, this is basically the axis, and that's the z-axis, right? Okay, yeah. And what's the moment inertia of this plate with respect to this z-axis, basically? Okay, yeah. So let's try very simple. I naught or G equal to R. This the region of integral, and R squared. Okay, and delta dA. So suppose that the plate has a delta equal to 1. So then this integral basically just become this one. So I'm going to use a polar because it's a circular disk region. So this is dA becomes R dr d theta. And R is from 0 to A, and theta from 0 to 2 pi, right? It's very simple. Okay. So the point is now for this calculation, I want to show you something after this one here. Okay, so you get basically the moment inertia with respect to axis passing through the origin for the plate with the radius of r is pi a to the power 4 over 2. Is that good? Yeah. Okay, so now here comes the next question. Now if I'm interested, here's a plate. I'm interested in the moment inertia not about the axis passing through the origin, but about an axis, okay, going through any locations at the boundary. Maybe it's here, doesn't matter. Okay, so basically we want a rotation of this disk about that axis L here. Okay, yeah. Is that good? So the previous one, it's about this axis, right? It's about this. And now it's about this. Okay, it's about this. Okay. So here there are two ways to do this. One is mathematically, just like what we did in the first question. So let's formulate the problem here. If this is the axis you're going through here, and in this formula, when we derive this formula is derived as a distance to an axis passing through the origin. So maybe what I can do at here is I'm going to restructure our coordinate system. So this coordinate system restructuring is like this. Okay. So this is x-axis, this is y-axis. And where's the axis? The rotation, axis rotation is passing through the origin at here. That makes sense, right? Yeah. Because I wanted to apply the formula that we derived using for the polar moment area. Okay? Yeah. And same thing for the circle. So this will be 2a at here, right? Be 2a. And then in terms of the moment inertia calculation, it's still about this axis passing through here. It's about the distance, right? You pick any point, okay? The distance r is to that location or that axis. So I naught will be double integral r squared times r dr d theta, right? See, this is still r squared, and this is dA, and this is the region r now, right? This region r. So this region r is a bit different from the previous region r, right? Because the previous one is centered around the circle, and this is here. Just like one of the assignments you're doing here, right? So when you have this kind of region R, I guess you want to use a polar coordinates, okay? Polar. So in order to use a polar, you draw a line, okay, out of this region R right here. First contact is 0. Second contact is over here. So this is your R max. So then how do I get the R max then? So this is theta here, right? So here's shortcut. connect these 2 points, you will end up with a right triangle. Then cosine theta equal to 2 divided by, cosine theta equal to R max divided by 2a, right? Divided by 2a. So cosine theta equal to R max divided by 2a, which means R max equal to 2a cosine theta. So 0 to 2a cosine theta. And inside here, this is R cubed, dr d theta. Theta is to sweep this line. To sweep this line to include the boundary, find the bounds for the theta. So when you're sweeping these reading lines here, where is the lower bound? The lower bound here. Is that right? And upper bound is over here. So for the lower bound, what would be the theta value, theta mean? At here, for this vector, what's the theta value from here to here? Yeah, exactly. And then for the upper bound is this, right? Yeah. That's how you evaluate, okay? But for this particular evaluation, you'll end up with a little bit of tricky ones. You'll end up with an integral of a cosine theta to the power of 4, okay? You can use formula, or you can look at my lecture notes. There is a very detailed integral by parts carried out for this one here, just for practice, okay? Yeah. So I wouldn't encourage you to do that, but you will end up with this here, okay? You end up with this. Okay, so the last minute I want to say is, but you do have a very neat theory, okay, which has nothing to do with the double integral, to calculate this moment inertia for this particular case. Can anybody enlighten me here? Or does that bring, these two? Yeah. Okay. Exactly, parallel axis theorem. Because the two axes are parallel, and we already have the moment inertia about this axis. The distance between the two axes is a. So parallel axis theorem says the moment inertia about the new axis equal the moment inertia about the axis going through the center of mass plus what? Plus AD squared. Okay, in this case. So ICM will equal to, as we calculated, pi a to the power 4 over 2. Area of the circle, pi a squared. D squared, D is the distance, is a squared. So together is, okay? Yeah. Any questions? All good?